Hey guys, so this is 6K General Solutions to Trig Equations. Before I go into the examples that we have on our booklets, I just want to give you a little bit of context in terms of what we're actually doing here. So in this case here, with this sort of example, we can solve this, but it hasn't specified a domain for us. Normally it might say from negative pi to pi, or from 0 to 2 pi, or something like that, but we haven't been told that. So if I'm going to solve it, I'd do something like this, and it's the same as I have been doing in the past. So I might use my little unit circle here. Root 2 on 2 for sine is going to be here, and that angle is pi on 4. So hopefully we know that from our exact values table. But also, it's down here as well, which would be 7 pi on 4. Okay, now note that it hasn't specified the domain again. So if we start here and rotate around the circle, let's have a look at the different solutions we can get. So x is going to be equal to, now I'm going to start here, there's our first solution, pi on 4. I can keep going around, and next solution is 7 pi on 4. This should be very familiar to you guys. If we keep going around, here's another one, so we're on our second rotation around. So that one's going to be 2 pi plus pi on 4, and then 2 pi plus 7 pi on 4. But it hasn't told us to stop at all, has it? So we can keep going around the circle. The next one's going to be 4 pi plus pi on 4, and then 4 pi plus 7 pi on 4. Again, it hasn't told us to stop, so we can keep going. 6 pi plus pi on 4. See how I'm never going to stop here? I'm just going to have an infinite amount of solutions because it hasn't specified when we actually need to stop. And that's only going around in the positive direction. If we were going around in the negative direction, one of our solutions would be negative pi on 4, and this one here would be negative 7 pi on 4. Negative because we're rotating around in the opposite direction. So more answers could be negative pi on 4, negative 7 pi on 4. We can keep going around, so negative 2 pi minus pi on 4, negative 2 pi minus 7 pi on 4. See how this is just going to keep going? There's no way we can write all these answers because there's never any stop to it. It's an infinite amount where they're going to keep going. So because we can't actually give all the answers, a way around that is to give a general solution. So I'll get rid of this here, and we can look at what I've got written here. So instead of giving all those answers that I was writing down before, we can give one kind of general equation. So for cos, your answer would look something like that. And this solution here encompasses all the answers that we were coming up with before. For tan, you've got this rule, and for sine, you've got these two. Okay, now you might notice that in each of them you have an n. So there's an n there, there's an n there, n there, n there. You're always going to have an n in your answer. What the n means is how many complete rotations around the circle you've done, or complete cycles. You'll see what I mean more so when I do a couple of these examples, but something that's really important is that n is always going to have to be a full number. There's no half rotations around, it's how many rotations you've completed. So if you're on your first rotation around, you've completed 0. When you're on your second rotation around, you've completed 1, etc, etc. But we can have a bit of a look at that later. Alright, so let's start with this one. Now this is actually the same as the example I gave you before, but we're finding the general solution. Okay, so because it's sine, we're going to be using these rules here. So all we really need to do is substitute this into here and then solve as far as we can. So that's what I'm going to do to start with. Okay, cool. So we've substituted our a in there. We can solve this bit now, can't we? So we're going to end up having 2 pi n plus, that's going to be pi on 4. Our other answer is this. And there's our solutions. So these little rules here can give us every single solution for sine, or for x when we're using sine. So what I might do is expand this out. You don't necessarily have to, but I just want to show you what it might look like. There we go. So we've got our solutions to that one there. Now we use those two rules because it was sine that we were working with. In this next example here, it's cos that we're working with. So we're going to forget about these two that we did use. This is what we're using. Now hopefully you notice that this is giving sort of two answers as well, because you've got your plus and you've also got your minus. So let's make sure we set this up correctly. So you might see that there's a 2 out the front. Hopefully you can remember from the exercise earlier, I can't remember the letter, we're going to move that 2 over to the other side. There we go. Now we can use our general rule just there. Now remember, this one has x equals. We're solving for 3x at the moment. So instead of just having x equals, it's going to be 3x equals. Okay, so it's half at 60 degrees, which is pi on 3. I should have done that step, but I'm not really going to worry about it for now. And what we need to do is make sure we get rid of this 3 as well. So we'll divide by 3 here, because it needs to be x equals. There we go. So there's our general solution for that one. Alright, so let's move on to the next example. We're going to be, in this example, using the general solutions that we find, so similar to what we did up here, but then we're going to find the actual solutions, so similar to what we did, or what I did in that first example earlier on that other piece of paper. Alright, again with this one, let's make sure we're moving that 2 over. Cool. Now we can use our general rule just here. There we go. Now we need to make sure we solve this section. And that one's going to be pi on 6, yeah. Alright, cool. So we have our general solution, but what we've been actually asked is to find the first 3 positive solutions. So this is when the value for n comes into it. So I want to find what the solutions are when n is 0. So that means we haven't completed any rotations around the circle. So if I make n 0, hopefully we can see that it gives us a couple of answers. This whole thing is going to become 0. So it gives us the answer of x equals negative pi on 6 and x equals pi on 6. Cool, it gave us a couple, except let's look back at the question. Find the first 3 positive solutions of the following. That's a positive solution. Is that a positive solution? It's got a negative out the front, so no it isn't. That's not something that we want. That's no good. Alright, so we've got our first positive solution. Let's see if we can get any if we make n equal 1. So we've completed one rotation around. So that means we're substituting n, or 1 into n. Okay, so we've got 2 pi minus pi on 6, so 11 pi on 12, on 6, sorry. And plus pi on 6, so that will be 13 pi on 6. Cool, so there's one positive solution, the next positive solution, and the next positive solution. So we've got the first three, and we're done. Let's move over to this next one, and we're doing the same thing. Again, we want the first three positive solutions, so we're probably going to have to find our general solution or equation. General solution is what you really should be calling it, and then find those first three by substituting in different n values. Alright, so because we're working with sine, we need to be using these rules just here. Okay, so let's solve for that and solve for that, which is the same thing. And to get a sine, or to get your vertical component of your triangle to be 1, we need to have the angle of pi on 2. And the same over here. Awesome. I'm not really going to bother expanding this bit out. I'm just going to leave it like that. We can see what happens. Alright, now we want the first three positive solutions. So I'm going to make n equal 0 to see the solutions that are involved in the first lap around the circle. What am I doing? That's supposed to be 1. Okay, so this one should give us 2 pi. Why am I making n 1? It should be 0. 0 and 0. Okay, so we can see that that is going to be 0 and then plus pi on 2. So that's one of our answers. Over here we're going to have 2 times 0, which is 0, plus 1 times pi, so pi minus pi on 2. We can see that this one has actually given us the same answer. There we go. So that's going to be one of our positive solutions. That's going to be our first one. Now, because these both do the same thing for this particular example, you might see why if you, I'm not going to explain it right now, but if you look deeper into what's actually happening here, I don't want to make the video too long, so I'm not going to explain right now. I might do that at a later stage. I'm not going to keep on using both of them because for this to get this solution of 1, there's only one answer around the circle. Normally there's 2, but this is a special one. Another special one might be 0 degrees or 0 radians for cos, because you'll have an answer of 1 as well. But I won't explain that whole thing right now. I'll just leave it for the time being. Alright, so let's substitute in 1 now because we want the next solution. And I'm only going to use that first formula here because they're both going to give me the same thing. Because if you expand it out, it would be the same thing. Alright, so we've got 2 pi plus pi on 2. So that will be 5 pi on 2. I've just seen that I'm making a mistake. So we're solving for 2x, not just x. So it's actually going to become, sorry to muck you up and go back a little bit. Plus pi on 4, and that's going to end up being the same thing. So we will end up having pi on 4 instead. Sorry. Alright, cool, there we go. So because I'm using the wrong thing over here as well, it should have been, that's gone, and then that is a 4. Right, so that's going to end up being 5 pi on 4. Cool, sorry to muck you around a little bit there. Alright, so we've got one solution because they're the same. We've got our second solution. Let's try to find our third solution. So I'm going to make n equal 2 now. Now I'm going to make sure I'm using the right rule, not like before. There we go. So 2 pi plus another quarter, that's going to be 9 pi on 4. There we go. So there's our first solution, there's our second solution, and there's our third positive solution. We are done. Alright, so let's look at these next ones, these next couple. We don't need to find specific solutions here, we're just trying to find the general solution. So the first thing I want to have a look at is what's happening here, and this is the first time we've done tan, but it's no different. We just need to use that the appropriate rule. You can see that we've got a 2 at the front here. Now that 2 is applying to the brackets here, so it's, you could say in a way that it's been taken out as a factor. So you could also write it like that if it makes it easier for you. I prefer to have it that way. I just think it kind of shows it in a little bit better way. Anyway, I'm going to move this root 3 over, but at the same time I'm going to expand this out as well. I don't know about you, but for me, I like it like that, so we can have it as that. I just expanded the brackets out, and we can move our root 3 over. Cool. So for this one here, when you use the tan rule, which is up here, but also we're not just solving for x, we're solving for this whole thing to start with. So it's going to end up being 2x plus pi on 2 equals, and we put the rest of our rules. So that's a mistake I made before. I put just x in there instead of having everything that was inside there. So try to not make that mistake. It can be reasonably common. Sorry. Okay, so we've put that into we'll put all the appropriate numbers into our general rule. And that's going to be pi on 3. Sweet, we're all set up. We want to solve for x though, okay, not this whole thing. So we're going to have to move this over to there. So we're going to move that over to that side. Now what am I doing? I shouldn't have put that negative there. That's in the cos rule. Alright, so we want to solve for x, so I'm going to move that over to there. So if we put these together, we need to make the denominator the same, so we can change the denominator to 6. So this is going to be 2 pi on 6 minus 3 pi on 6, which is going to give us minus pi on 6. There we go. Last step, we need to make sure we're solving for just x, so we'll divide both of these things by 2. So x should be pi n on 2 minus pi on 12. Cool. Alright, now this one over here, I might just leave you to do it because it's done in the exact same way as this one was done, except using the cos rule. So I don't want to make the video too long. So have a go at that one yourself. The answers you should get though, because I want to make sure you know whether you're getting it right or not. X equals pi n plus 7 pi on 12. And x equals pi n minus pi on 12. So that's your general solution. We're going to flip over and try this exam or past exam question now. There's only one this time, or for this exercise anyway. Right, now we've just been finding general solutions. It's what we've been asked for. We could use the sign rules to work this out, except this is a multiple choice question. I think it's best to save as much brain power as we can. I'd type this straight into my CAS. Now, after all we're doing is trying to solve for x, aren't we? So, on our CAS, we could use the solve function. So I'm solving. The rule that we have is up here. Right, so there's our rule. We need to tell the calculator that we're trying to solve for x. So we put comma x in there. Alright, now you press enter and it should give you a general solution. So if you pressed enter, you're going to end up getting this. Now telling you now, the n might not look like that. It could, I can't remember exactly, but it might say something like C1 or D2 or whatever, or N something. It just means N. So it might look a little bit more complicated, but whatever unknown that it gives you, just change it to N, because that's after all what it means. Now we found a few general solutions before. They didn't really look like this, did they? Okay, so this makes it a little bit confusing, but what I'd like to do is maybe just change what this looks like a little bit. All right, so if we expand this set of brackets out, what you're going to end up having is this under here. Now you guys are going to be able to do this, no worries. Alright, so I just split them up and made it two different fractions when it could have been together as well. We're going to be able to see that the 4s are going to cancel out here. Four n minus pi on 4. Okay, pi n minus pi on 4, sorry. So that looks a little bit more familiar to what we're doing before. Let's look at what the answers are. Alright, now does this look like anything that's going on up there? This rule's the same as that, isn't it? Okay, so that's the one that we're looking at. If you confuse it all by this n and then z, that just means that n can be like integers, so your whole numbers 1, 2, 3, 4, which is something that I mentioned before, and it is in your notes as well. So if you read through the bit in this booklet, you should see that should clear it up a little bit for you. But our answer is definitely A.